My thesis is about the jet noise diagnostic by using a massive microphone array, which is mainly founded by the Jamaican project and supervised by Marco Raiola, who you probably all know, and Luis Aspicueta, who belongs to the signal theory department. So let me start with the motivation that is behind this work. And to frame this problem, I'm going to use the aircraft traffic map of Amsterdam City. As you can see, the blue lines and red lines correspond to arrivals and departures. In the noise emission map that you can see on the right, it's clearly that takeoffs generate more noise than landings. And to give you a clear idea, I'm going to make you hear what a takeoff sounds like. As you could hear, there are several noise events happening at the same time. And well, this is quite difficult to disaggregate and separate all the noise contributions. There are some techniques, such as the beamforming, that allows us to localize where the noise emission is located, and along all the frequency domain and also time domain. By using this technique, Nesbrid could present the noise distribution, and it turns out that the fan, together with the jet, were the most noisy contributors. I'm talking about the takeoff phase. Turbulence is a very difficult and a complex problem to solve, but the noise produced by turbulence is complex as well. But the literature says that noise is generated in the jet because of the large scale structures and also small scale structures. And well, they both produce a different kind of noise. And in the industry, you can find several solutions to these problems, such as the passive solutions. You can see the chevron, where it uses accelerations around the jet, and also some corrugations that you can implement in the internal part of the engine, as well as the active solution, as Luca already presented, that is based basically in air injection to modify and control the airflow. My thesis is mainly divided in these three stages. The first one is the test site that I'm going to use, where I'm performing my measurements. And this is a jet facility that I'm going to get into detail later. The next one is the development and the building of the low-cost massive acoustic camera. This is something that it hasn't been done before, because there are some groups that they do the same, but with a lot of money. And lastly, I'm going to use some classical methods of beamforming to localize where this sound is being generated. The novelty of this thesis is that since I'm using a large amount of microphones, I'm going to get a very high spatial resolution. I also wanted to highlight how I dedicated my time along these 18 months. And well, of course, I spent some time reading and adequating the anechoic chamber. And well, prototyping, this is a task that it took me longer than I expected at the beginning. As you can see, the jet facility is, what we have here is a traditional anechoic chamber that is downstairs in building 7. And we placed the jet pointing to that direction, but the first challenge that we had is that there is sort of air recirculation. This is because the anechoic chamber doesn't have any exhaust section in order to extract all this air. To solve this, we proposed the implementation of the air collector and a dissipation cavity. But since we are modifying the acoustic properties, because we are going to modify the dimensions of the anechoic chamber, we assessed by analysis and also performed some measurements to see what was the state before and after the intervention. Then we could determine by the free field qualification that up to a radius of 1.4 meters, we can fulfill this physical law. And for this dimension, we're going to have some reflections that affects our measurement. All this job was in collaboration with Luca Franceschelli and it was presented in the acoustic conference. Of all the development boards that I had investigated, the Beagle Black was the one that best covers our technical requirements. Mainly the low cost, well, this is sometimes a tricky word because it not necessarily means that the development cost it has to be low as well, but it was totally the opposite. And well, it's just around 55 euros and very cheap. It has a very powerful microprocessor that can handle multi-channel recordings. And with the strategy to make it up bigger and a massive microphone array is to make a system modular. And by leveraging some characteristics of the microphones, we can also think about the multiplexing of the signals. As I mentioned before, this is a task that took me very long time, more than I expected, and I had to write some codecs, some drivers. I had to compile a kernel, a new image into the Beagle Black, so it was a hard task. The microphone that I'm using is a microelectrical mechanical system that already delivers a digital signal and also uses the TDM protocol, which allows us to multiplex one microphone next to the other and using one single data line. This means that if the Beagle Black can handle 4 serializers, I mean 4 of these 16 group of microphones, we can record with one module up to 64 microphones. If we multiply this by 16 times, then we can reach the 1,024 microphones. All the technical specification and the PCB design was done with collaboration with Jorge Ortigoso, that he is also present here in the audience, and presented in the Acoustica conference. The acoustic performance of the square grid array, I'm going to present it in these 2 weeks. And these are all the design criteria that I took into account to make this module scalable. This is inspired, and it uses the underbring spiral array that is very, very popular it's in the state of the art. And I run some simulations in order to get what is the best configuration of the spiral parameters. One can expect that this configuration varies in all the frequency domains. So what we want is to have something that responds quite stable. There are some parameters that allow us to assess the performance of the microphone distribution. But in the end, since we are using loads of microphones, this distribution is not so critical. But anyways, we pick the optimal case. So far, I've developed 2 beamforming and classic techniques, such as the delay and sum and conventional frequency domain. They both have pros and cons, and well, they are solved in an analytical way, but they are thought to be used with a limited number of microphones. And my thesis is not only, I mean, the main scope of my thesis is not just proposing a better beamforming algorithm. I think we can go further. And to finish, well, these are the next steps. And since I'm using a large number of microphones, there is a big statistical data. And even if the signals are not in the best quality, because it's a cheap microphone around 3 euros each. And well, I'd like to use machine learning to identify all the events that happen in the jet. And well, the goal in the future would be to predict and model from other measurement techniques, such as the particle image velocimetry, and correlate with these map sources, which is what I'm doing with the beamforming. These are all the achievements that I've done so far. Some conference proceedings, some conference presentations, some workshops, and outreach activities. Well, I could collaborate, as you can see, with many people from here, from the department, as well as Luca Schneeberger. We did also an activity for Semana de la Ciencia. And that would be all.